That is the fundamental idea. So you take your prior ratio, multiply by your likelihood ratio, and you end up with your posterior ratio. And that kind of talks about that. So here is another example which I want to talk through on the screen, which illustrates this exact same idea. And actually this is moving into the idea of forensic statistics, okay? So one of the ways which Bayesian statistics is being used is in forensics, and in actually, can you tell whether somebody has actually committed a crime based on the evidence that is in front of you, okay? So let's imagine that a crime has been committed, okay? And you go out and you realise that there's 1,000 people that could have committed this crime. There's 1,000 people that could have committed this crime. And you then find a sort of unreliable witness, maybe the witness was drunk or something, okay, who then sort of points out that this person, this one suspect, was the one that committed the crime, okay? So you started off with 1,000 possible perpetrators, and then one of these people gets pointed out by an unreliable witness that they actually committed the crime, okay? So in other words, your prior ratio, let me get rid of all of this. So in other words, your prior ratio, in other words, the probability that this suspect committed the crime was what? Exactly, or 1 in 1,000. Absolutely, yeah, 0.1%, okay? But then some new evidence comes to light, okay? And typically the new evidence, and the way that this is typically used, is in the form of DNA evidence, okay? So let's suppose that there's DNA evidence that's found at the screen, okay, or found at the scene, okay? And this DNA evidence matches the suspect. Okay, matches the suspect which you originally thought. Now, you need to come up with a likelihood ratio. You need to come up with a new evidence, a new ratio, based on this evidence here. Okay? Now, the way which DNA evidence, the way which the likelihood ratio is built from DNA evidence is like this. Okay? So it's the probability that the DNA, of a DNA match assuming the suspect committed the crime. Okay? So if this suspect commits the crime, what is the probability that the DNA will match this person? Okay? And then you divide that by a probability of a DNA match assuming somebody else committed the crime. Okay? Because of course what you have to remember is that DNA is a genetic mutation. Okay? It's just genetics. Okay? Now by chance there should be that DNA should match somebody else, doesn't it? Because it's not unique. Like, think about it. There's 7.7 billion people in the world, okay? Just purely through genetic mutation, it should be the case that that DNA should match somebody else, okay? Just purely by chance.
Isn't it different DNA?
Yeah, absolutely. It's a really low probability, but there is still a chance. There is still a chance, okay? So your DNA will almost certainly match somebody else because there's so many people in the world, okay? Because remember, DNA is like mutated, okay, through sort of genes and through genetics, okay? And eventually, you end up with 2 DNA samples that purely by chance, you just ended up with the same DNA sequence, just purely by chance.
You think there is a chance that I can be accused of something?
Absolutely right, yeah. So just because DNA matches you, because it matched the scene, like, there's still a probability that you didn't commit the crime, but because DNA has been mutated, it just matches somebody else, yeah? So DNA evidence, like this is the thing with DNA evidence, they have to use Bayesian statistics in order to work out, well, actually, what is the probability that this DNA is correct, okay? So let's suppose, okay, by the way, this thing on the bottom, the probability of a DNA match assuming somebody else committed the crime. So Mohammed, if the DNA matched you, but it was somebody else that committed the crime, we call this a random match probability, a random match probability. Okay, it's just basically by random chance, the DNA just matches you, okay? So this is the thing which you want to work out. So let's suppose we have, 1. So 1, if you get a DNA match and it's you that committed the crime, it's a certain chance. Okay, so it's 1, right? Then you think about what is the random match probability? What is the probability that the DNA matches you even though you didn't commit the crime? This is the thing which forensic scientists need to work out. Okay, and I mean, let's just say it's 1 in a million. Now, by the way, this is still quite high. This is still quite high, yeah? Because there's 66 million people living in the UK. So if this probability down here, so in other words, it comes back, it matches you, even though you didn't do it, okay? That means that there's 66 people in the UK that will have a match to this DNA, which is quite high, yeah? It's quite high, right? So in actual fact, like if this is like 1 in a billion, then that means that there's 7 people in the world, or 7.7 people in the world who will match this DNA. Okay? So the whole point is you are trying to work out what this random match probability is. This is what forensic scientists need to do. Okay? And in actual fact, if it comes back as like 1 in a billion, as soon as you combine it with something like this, forensic scientists tend to say, hey, that's enough to make a conviction. Okay? So, in other words, if you so 1 in a million comes out as a million, right? So 1 divided by 1 in a million comes out as a million. So in other words, when you combine this stuff together, you come back with, well, 1 in 1,000. Let's do this. 1 in 1,000. Remember that was the probability that the suspect committed the crime. So you start off with 1,000 perpetrators. Somebody pointed out a suspect. Probability the suspect committed the crime was 1 in 1,000. Okay? You then, according to Bayesian statistics, need to multiply that by, well, 1 divided by 1 in a million, which is, of course, just a million. Okay? Now, if you multiply these two things together, what do you get? 1,000. Okay? Now, in general, the higher this number is, the higher your posterior belief is, the more chance there is that this suspect actually committed the crime. Okay? But it all depends on what this was. All depends on what this was.
This was given.
Sorry?
This should be given, like the new evidence?
Yes, exactly. So in other words, there's 1,000 chance, so whatever that is, the higher the number is, okay, then the more chance there is that this suspect actually committed the crime. Okay? So you can see you start off with a prior belief. In other words, an unreliable witness comes forward, points out a suspect, so thinks that you did it, Mohammed, right? And then you look at the DNA evidence and say, well, actually, there's a 1 in a million chance that the DNA should match Mohammed, even if you didn't do it. Okay? And obviously, the higher this number is, then the lower this number will become. Sorry, the higher this number will become. Yes. Yeah? And then you can work it out. So the higher this number is over here, the more chance there is that you actually committed the crime. Okay? So, this is the idea. However, this idea of multiplying prior beliefs by new evidence, okay, like new likelihood ratios, has actually been banned in UK courts. So you are not allowed to combine prior ratios and likelihood ratios together in UK courts, okay? And if you want to read about that, there's a case, I think it was 1997. There was basically a Cambridge or Oxford professor who came in, professor of Bayesian statistics, who came in and said, well, this is the way which you should combine these two numbers together. It told the jury, this is the way which you should combine these two ratios together, okay? And the jury got so confused that it ended up being that this was just unreliable, okay? It just became unreliable because the jury didn't understand what they were actually doing, okay? So therefore, it's now the case that in courts, it's been completely outlawed. You are not allowed to multiply these two things together. You can talk about this idea, you can talk about likelihood ratios, but you can't talk about multiplying these two things together. Okay. So, can I ask you to take a break for 10 minutes? Okay. So this is forensic statistics. It just shows you that Bayesian statistics is really, really useful. Okay. Hopefully you've got the idea that you end up with you start with a prior belief, what you initially believe, multiply it by a likelihood ratio, something which you now believe to be true, new evidence, and you end up with a new belief. Okay.